So in this video, I'll continue the discussion on transformer insulation power factor. So as I stated in the previous video, so the transformer insulation can be modeled as a capacitor in parallel or in series. The parallel combination is typically used in parallel with a resistor. So then when you apply current AC voltage, so some total current will flow, some of it, if there is leakage, in other words, contamination like I talked about, moisture, any other things that makes the insulation not perfect, then you're going to have some resistive current flowing, and that's what's going to cause the losses. Then you're going to have capacitive current, which is what it should be if there will be capacitive current. So then this resistor here, which is not a typical resistance, like what you see in a conductor. This is just a representation of the leakage current, that because the insulation is not perfect. So then it's going to cause some losses. And we know power factor equation, it's watts divided by voltage times amps. Like whatever voltage you apply, whatever current is circulated. So for insulation, we want this to be 0, but we know it's not going to be 0. So it's going to be some value other than 0. But we want it to be as small as possible, because then we know there are no problems with insulation. And I'll talk about in this series of videos, I'll talk about power factor, like the different tests that can be performed, when you have high voltage, low voltage, tertiary winding, and there are different setups, So inside a transformer, so you have, for instance, this is a tank basically. So this is the tank, and this is kind of like top view, or just kind of give an idea. So these are bushings, and these are the terminals, and this is the low voltage side. So the same thing, we have the bushings. So in this case, I'm showing the windings. So you have 3 windings. So winding 1, 2, 3 that connected in a delta. Just as an example, it can be any connection. This is the low voltage connected as Y. So here's winding 1, 2, 3, and brought to bushings, terminals. And this is so this might be, so H1, H2 bushing, H3. This would be X1, X2, X3. Then the tank is connected to ground, because there. So transformer core is grounded. So I have a picture here that I took from this site here. So you have here's the core limb 1, core limb 2, and here's the third. This is a 3-limb core. Then you have the yokes. So this is the top yoke. This is the bottom yoke. And the yokes basically connect the limbs, because the core has to be a complete circuit. Then you have these frames here, or core clamps, to keep the core together, because it's laminated. This is just one, there are different technologies. Then what you would do, what they would do, they would stick a strap inside between the laminations. So it's from aluminum, for instance, aluminum strap. Then they would bring that to, so for large transformers, typically they bring that to a bushing. So core bushing, then they will ground that bushing externally. That's the best practice. For smaller transformers like pad mount, pole mount, what you see in distribution systems, Typically, it might be grounded internally, but then if you want to test the core ground insulation, as I'll talk about that later, or even power factor, it can be, there are certain tests you cannot do unless you remove that. So, and this just shows kind of the windings. This is a core form, so the windings are concentric, then they're wound around the core. So the core would be grounded basically. So transformer core is grounded, the tank is grounded, then transformer insulation is made up of, you have oil if it's filled. So I'm only talking about oil filled here for simplicity. You have paper inside, you have pressboard, you have tape, wood, enamel on the conductors. So there's so many types of insulation, and all that kind of is required for insulation purposes, So during insulation power factor test, all bushings, so what you do, you connect the terminals together. So you put a wire or a conductor basically. Then you do the same thing for the low voltage. And if you have the XO, so typically the neutral bushing will be grounded, so you have to remove that ground. So XO is isolated from ground. Terminals are shorted together, then energize bushing winding leads. So basically what you do, so you can energize because you can measure from high, then you measure from low. And again, I'll talk about different tests later, but this is just kind of explain the test setup. So then what you do, you apply AC voltage. So for instance, you apply the hot lead to the bushings here. Then what you do, you can ground the low voltage if either grounded or ungrounded. And again, there is like an ungrounded specimen test. There is grounded. So there are different because if you don't want to include the ground in the measurement, I'll talk about that later. So you energize the bushing. So the bushings are energized, the winding leads, and also the windings are all shorted because we want to minimize any inductance impact. So what you see here, and this is to ground from the windings to ground in this case. But as you can see, from the bushings, leads, windings, they are not connected to ground, so that it's an open circuit basically. So that power factor should be very small, theoretically speaking, if everything is good, and so if there's no moisture, no contamination, all the things I talked about. So all the insulation, or I guess, sorry, like if you take the windings, then the bushings, the bushing leads, conductors, the tank core frames, then the insulation, oil, paper, pressboard, porcelain, or polymer. It depends on what kind of bushing you have, etc. All that makes up the capacitor. Again, if you go back to the model, because when you apply voltage, it's an AC voltage, and that voltage will depend on the withstand of the system you are testing. For large transformers, typically 10 kilovolt or kV, so typically 10 kV AC voltage is applied. However, if the windings you are testing or you're energizing are rated 480 volt, for instance, you cannot apply that. You have to be careful not to exceed the withstand of the windings. But for large transformers, 10 kV is typically applied. But then basically, if you take the windings, then the insulation, because when you energize the windings, they are isolated from ground. They are not connected to anything they're not completely into circuit. So if everything's perfect, this here should not exist. It's just a capacitor, because the only thing that completes the circuit is the capacitance from what you're energizing to ground, basically. But if there's contamination, moisture, then this resistance will consume some watts, which is in the form of losses. Then you go back to the definition of power factor: watts divided by voltage that you apply, current that you measure. So you're going to apply some AC voltage, some current will flow, some of that current will go through here, some current will go through the capacitor. So obviously, the worse the imperfection of the insulation, whether there's moisture, contamination, the higher the watts will be. That means power factor will get larger. You don't want that. We want the power factor to be as small as possible. Typically, for power transformers, typically you want that to be smaller than 0.5%. This is just to give you an idea. So for distribution type transformers, with mineral oil, distribution transformers, what I mean by that, pole mount, pad mount, like where the low voltage, for instance, is less than, say, 600 volts or 800 volts, less than 1,000 volts. Let's just make it very simple. Then it's going to be, it should be typically less than 1%. But if it's ester or FR3, any biodegradable insulation, typically those, they have a higher power factor. So then you have to refer to the manufacturer, what is accepted, what is not. Mineral oil has been around for years, so it's well understood. So there's like a typical power factor is well established. So large transformers with low voltage, for instance, 2 kV all the way up, typically 0.5% is, or less than 0.5% is a lot easier to accomplish. But anyway, so the insulation, basically, you will have some leakage, or in terms of watts, and that will cause that power factor kind of deviate from zero, because we know the insulation is not perfect. So the core is grounded. The frame also might be grounded as well. So the frame might be, might be insulated the frame might be grounded internally, or it might be brought out to a bushing. Typically large power transformers, you would have 2 bushings, one for core ground and one for the frame. And that's, again, a good practice. That way, if there is an issue, and I'll talk about core ground resistance later at a different video, because then you can kind of determine where there is an issue. Is it the core, or is it the frame? But the frames, they have to be isolated or insulated from the tank, because the frames, or the core and coil. So basically, this assembly here, because you have the windings, you have the core are held by the frames. It has to be dropped inside the tank, so they have to be insulated from the tank, because the tank is grounded. All right, so thank you, and I'll continue the discussion on power factor.